Binary logistic regression with one continuous predictor or one ordinal predictor in JAMOVI. Binary logistic regression with a continuous predictor in JAMOVI. Binary logistic regression is a statistical method that can be used to find a relationship or association between two variables. One of the variable is the outcome, or it is called a response variable or the dependent variable. This outcome variable have to be binary. Binary variable have only two levels in it. Have the diabetes, no diabetes, heart diseases, no heart diseases, yes or no, smokes, doesn't smoke. The second variable is the predictor, or alternatively it is called the explanatory factor or variable, the independent variable or the exposure variable. The main reason to use this test is to find out whether there is association between predictor and outcome, and whether the predictor can predict the outcome, and whether the variation in the outcome can be explained by the predictor. The predictor can be a continuous variable, can be binary variable, can be a multinomial variable, or it can be ordinal variable. Continuous predictor is a variable that have a scale data in it, measured at either an interval or a ratio level. Here in JAMOVI data sheet, I had inserted two variables. The first one is the age, the second one is the heart diseases. There are 100 cases in this data sheet. So here we have two variables. The first variable is age, and it is a continuous variable. It's measured at a scale. And a second variable, which is the heart diseases, is a binary variable or binomial variable, as it has only two levels in it, whether you have the heart diseases or no heart diseases. To find out whether there is association between age or increasing age with the probability or the possibility of having heart diseases, then the binary logistic regression can be used, as the outcome here, which is the heart diseases, is binary, and the predictor, which is the age, is a continuous. Before we proceed to the test, let's look at some descriptive statistics by clicking on exploration, then descriptive. In this window, drag the age into the variable section and the heart diseases into the variable section. As shown here, I'm going to trim some of the things here, like I don't want the median, the mean, and I don't want the standard deviation. As shown here in this table, there are 100 cases, no missing values. If I click on the frequency table or tables, again a second table is generated. So in the first table, the age has a minimum value of 18 years old and a maximum age of 94 years old. For the second table, which is the heart diseases, there are 44% of the cases have no heart diseases and 56 have heart diseases. To find out whether the age can predict the heart diseases, we will do a binary logistic regression, as the criteria or the condition is set for that test. To do that, click on regression here, scroll down to two outcomes, binomial, and in this new window here for binomial or binary logistic regression, drag the age, which is a predictor into the covariate section, and the outcome, which is the heart diseases, into the dependent variable. Spontaneously, a few tables are generated, but let's scroll down here and see if we need to select any of these options here. For the reference level, no heart diseases is set at a reference level, or we can swap it to set the reference category as heart disease, but here we'll stick with no heart diseases. For the option of assumption check, we'll not look at it at this stage. Model fits, I'm going to tick on the Cox Snell R Square, and also the other one for R Square here. For a model coefficient, definitely we'll look at the odds ratio to generate an odd ratio as shown here. We will give it also a confidence interval for that odds ratio. We'll not at this stage look at these. For the estimate marginal, nothing to select from. For prediction, let's go for classification table. And finally, for save, we'll stick what we have in the output. Again, as shown here, from the output for the binomial logistic regression in JAMOVI, multiple tables are generated. The first table here is the model fit measures. We're going to look at this R square here. This R square, which is equal to 0.774, indicates, or it means that 77.4% of that variation in the outcome, which is heart diseases, can be explained by the age predictor. So there is association between the age and the heart diseases or the outcome. Moving to the second section here as shown in this table, it is the model coefficient heart disease. We will ignore the intercept value, but we will look at the age values. Here is the estimate for coefficient. Here is the standard error, the z-score, the p-value, the odds ratio or exponential b, and the 95% confidence interval. And a footnote is produced here, represent odd ratio versus no. So it is the odds, log odds ratio of heart diseases to no heart diseases. From the p-value here, it shows that there is a significant association between the age predictor and the outcome, which is the heart diseases. This is also confirmed by the 95% confidence interval for the odds ratio, in which the 1.2 fit within the upper and lower limit. So to start with, there is a relationship between age and heart diseases, or chances or likelihood of having heart diseases. The way to interpret this table is that for each unit of age, which is 1 year, there is an increased odds of 1.2 of having heart diseases, and this association is significant. In another way, for every year increase in age, there is a 20% chances of having heart diseases. 20% is calculated by subtracting from 1.21, and that will end up in 0.2. Multiply that by 100, so it is 20%. So there is, from this table, there is an increased chance of developing heart diseases with increased age. So age is a factor that can predict or explain the variation in the outcome, which is the heart diseases. So this is the way to perform binary logistic regression with a predictor that is continuous in JAMOVI. Binary logistic regression with ordinal predictor in JAMOVI. Here in JAMOVI datasheet, I had inserted 200 cases. and there are two variables. The first one is the age category, the second one is diabetes. So the diabetes is a binary variable because it has only two levels in it, whether you have diabetes or no diabetes. Age, though age is continuous, but here it is classes or categories. Category from 16 years old to 24, and then the second category is from 25 to 45, the third one is from 46 to 70, and the fourth one is greater than 70 years old. So there are four categories here, youngest one to the oldest one, though it is age, but it is in category and there is order in it, youngest, older. So this is a ordinal variable. It is categorical, but it is ordinal, more precisely ordinal, as it has order in it. So to find out whether there is association or relationship between the age category and the diabetes, and whether this predictor, which is the age category, can predict possibility of getting diabetes, or the outcome, which is diabetes, variation in it, can be explained by the age categories, then binary logistic regression can be used, as the outcome here, which is diabetes, is binary and the predictor is ordinal. Before we proceed to the regression, let's look at some descriptive statistics. Click on exploration and then select descriptive, then drag the age category into the variables, the diabetes into the variables, tick on the frequency tables. Let's get rid of, since both of them are categories, we don't need the mean and the median. We remove the standard deviation, we keep the minimum and the maximum. From the output for the descriptive analysis, there are 200 cases. So both variable, there are 200 cases and no missing cases as shown here. The age category is assigned values 0, 1, 2, 3. The 0 assigned for the age category from 16 to 24. The value 1 assigned for 25 to 45, and value 2 assigned for 46 to 70, and 3 for anything greater than 70 years old. The second table shows the frequencies in each category. So as we have 4 categories here, there are 50 individual or cases in each category. For the binary outcome, which is a diabetes, there are 81 cases of those who have diabetes and 119 without diabetes. So those who do not have diabetes have a higher proportion. To do binary logistic regression, click on regression, scroll down to the 2 outcome binomial. Since this these data fit perfectly to the binary logistic regression. In this window, diabetes is our outcome, so we'll move it to the dependent variable. And since the age categories is factors, we'll keep it into the factors. We could move it to covariate, but we'll keep it here into the factors, and the age category is best fit here. Let's select some of the options here. We'll click on the reference levels. Since we have here 2 variables, both of them have categories in it. The diabetes have either you have diabetes or yes or no. No will be used as a reference category to compare to. Age category, which is from 16 to 24 years old, will be used as a reference category to compare to. Moving to the, I'm going to skip the assumption checks. Moving to the model fit, tick on the Cox and Snell R Square and the other R squares. For model coefficient, I'm going to tick on the odds ratio and the 95% confidence interval. For estimated margin, no selection. For prediction, no selection at this stage. Looking at the output here, we have two important tables. The first table is for model fit measures. Looking at the R square here, it shows that a value of 0.255. This value means that 25.5% of the variation in the outcome, which is diabetes, can be explained by the predictor, which is the age categories. Moving to the second table, which is the model coefficient for diabetes, we used those who with no diabetes group as a reference group. And for a predictor, which is the age categories, all the three are compared to the reference category, which is 16 to 24. So this is the reference category here. In the table, we're going to ignore the intercept, and looking at the footnote here, it says that the odds of diabetes for yes and no. Values here is estimate for the coefficient, the standard error, the z-score, the p-value, the odds ratio, and the 95% confidence interval. So there are two levels here for checking significance. P-value, any p-value less than 0.05 will be considered as significant, and 95% confidence interval, when the odds ratio fit between the upper and lower limit, then it is significant. So here from this output, we can see that there is a significant association between diabetes and the predictor, and even with each categories of the predictor. So there is association. The outcome, variation in the outcome in diabetes can be explained by the age category. So age is a factor that can explain whether you will have a chance, probability, likelihood to get diabetes. The way to interpret this table is that looking at the first category, for those individuals who are in the age range of 25 to 45 years old, have an increased 3.1 odds of having or developing diabetes compared to the younger generation, which is, or younger individual, 16 to 24. So older individuals have a higher chances or are more likely to develop diabetes than younger one. For the second category, which is from 46 to 70 years old, those individuals in that category have an increased 7.3 odds of developing diabetes compared to the younger group. So with increased age category, the odds increase or increases. So that means the elder people have a higher likely chance of developing diabetes. Looking at the final category here, those who greater than 70 have the highest likely or chances of developing diabetes compared to the younger group from 16 to 24. And all these findings are significant. So this is the way to perform binary logistic regression with an ordinal predictor in JAMOVI. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, JAMOVI, R Statistic or Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, JAMOVI, R Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.